In graph theory chapter, I already finished graph terminology and special types of graph, reprinting graph and graph isomorphism, connectivity, Euler and Hamilton path. Next I will discuss planar graph. After planar graph, last topic is graph coloring. So today I will start planar graph. So what is planar graph? Any graph that we can draw in a plane without any crossing is called as planar graph. Definition 1. A graph is called planar if it can be drawn in a plane without any edge crossing. Such a drawing called a planar representation of a graph. If a graph we can draw in a plane, it's called as planar graph and there should not be any crossing. Now example 1 is K4 planar. K4 means complete graph having 4 vertices. So this is the graph. Is it planar? There are crossing. Here is a crossing. But can we rewrite this? Can we redraw this graph? Yes, we can redesign this graph. This edge we can draw outside. So after redesign, we'll get this graph. And here there are no crossing of edges. Hence K4 is a planar graph. Yes, we can redesign it without crossing of edges. Next example 2 is Q3 planar. This is our Q3. Is it planar? So there are edge crossing, but can we redesign this without any crossing of edge? Yes, we can redesign it. So this is after redesign. As you can redesign, hence it is planar. So we found K4 is planar and Q3 is planar. Next example 3 is K33 shown in figure planar. K33 means bipartite graph. One set contains 3 vertices, other set contains 3 vertices. So this is the diagram: V1, V2, V3 in one side, V4, V5, V6 in other side. So is it planar? There are no way we can redesign this graph without any crossing of edge. Hence this is non-planar. We cannot redesign it. Okay. So this K33 is non-planar. Next, Euler's formula. So before Euler theorem, first understand what is region. We can partition a graph into different region. There are 2 types of region. One is bounded, another is unbounded. So outside region is called as unbounded, whereas a region within the edges called as bounded. A planar representation of graph split the plane into regions including unbounded region. So here is an example of graph having different region. So here R1, R2, R3, R4 and R5 are bounded region, whereas R6 is a unbounded region, that is outside. So R6 is all outside region. Okay. R1 is just within these 3 edges. Now theorem 1, Euler's formula. Let G be a connected planar simple graph with E edges and B vertices. Let R be the number of regions in a planar representation of G. Then R equals to E minus V plus 2. Now take this example. Here R equals to 6, E equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 edges and B equals to 1, 2, 3, 4, 5, 6, 7. So B equals to 7. R equals to 6 equals to 11 minus 7 plus 2. 11 minus 7 is 4. 4 plus 2 equals to 6 and R is 6. So here this satisfies R equals to E minus B plus 2. Now example 4. Suppose that connected planar graph was 20 vertices and each of degree 3. Into how many regions does the representation of this planar graph split the plane? So it is asking what is R and number of vertices equals to 20. Each vertices degree is 3. First we need to find number of edges. 2 into E equals to sum of degree of vertices. Now each vertices degree is 3. Okay, so 20 into 3 equals to 2 into E. 2E equals to 60 and E equals to 30. We found number of edges equals to 30. Then we'll find R. So R equals to E minus B plus 2. 30 minus B, number of vertices equal to 20 plus 2. 30 minus 20, 10. 10 plus 2 equals to 12. we found r equals to 12. Now corollary 1, if G is a connected planar simple graph with E edges and B vertices where B greater than equals to 3, then E must be less than equals to 3B minus 6. Let's first prove this corollary. So 2E equals to sum of degree which is greater than 3 into radians. So if we take this 3 into left side, 2 divide 3E greater than equals to r, and in place of r we can write e minus b plus 2. So e minus b plus 2 is less than equals to 2 divide 3e. Now take this e into left side and take b minus 2 into right side. So e minus 2 divide 3e will be e divide 3 which is less than equals to b minus 2. Now I can take this 3 to right side. So it will be multiplied with b minus 2. E will be less than equals to 3 multiplied b minus 2. So 3b minus 6. That same is in corollary 1. Now example 5, so that K5 is non-planar using corollary 1. So we'll use this corollary 1 and we'll show that K5 is non-planar. K5, it's a complete graph having 5 vertices. Then how many edges will be there? 5 multiplication 4 divide 2. So it's 10. So in K5 there are 5 vertices and 10 edges. E equals to 10. B equals to 5. Now we'll check is this planar or not. So E 10 should be less than equals to 3 multiplication 5 minus 6. 3 multiplication 5 is 15 minus 6. It's 9. Is 10 less than equals to 9? No. As 10 is not less than equals to 9. Hence K5 is non-planar. If E will be less than equals to 3B minus 6, then it's planar. If E is not less than equals to 3B minus 6, means it's non-planar. Next, corollary 2. If a connected planar simple graph has E edges and B vertices with B greater than equals to 3 and no circuit of length 3, or you can say no cycle of length 3, then E less than equals to 2B minus 4. You can prove same way as corollary 1. Now let's see one example. Example 6. Use corollary 2 to show that K33 is non-planar. K33 is a bipartite graph. K33 there are 6 vertices and 3 multiplied 3 there are 9 edges. So we got number of vertices equals to 6, number of edges equals to 9. E 9 should be less than equals to 2 multiplied by 6 minus 4. 2 multiplied 6 is 12. 12 minus 4 is 8. Is 9 less than equals to 8? No. Hence K33 is non-planar. If in a graph there are no circuit of length 3, you can use this formula to check whether the graph is planar and non-planar. In today's lecture I discussed what is planar graph, what is non-planar graph, Euler formula and 2 corollary. In next lecture I'll discuss this theorem, and if this lecture is helpful for you, please like, share and subscribe. Thank you.